In this module, we're going to look at a maximization model example. So, during this session, it is my goal to provide you with the skills required to formulate a linear programming model. So, the first example we're going to look at is the Eager Beaver Woodworking Shop example. So, this shop is a small colonial American woodworking shop specializing in the creation of antique furniture. The shop is currently producing antique chests and antique tables to be shipped to various retailers across the country. So we can see here are the two products that they produce. So the two primary resources used are wood. They use both American and Army chestnut, and also labor. So given the fact that limited resources exist for manufacturing the products, the company wants to know how many chests and tables it should produce to maximize its profit. And this type of problem is often referred to as a product mix problem, and it has applications in many fields. So initially, you might look at this problem and say, well, this is a fairly easy, straightforward problem, because obviously you're going to you would want to produce the product that yields the highest profit or the highest revenue. So you look at these two products that are produced, chests and tables, and you would say, well, chests yield $2,900 per item, and tables are only $2,300. So let's just make all chests. Well, the problem is when you look at the resource requirements. So a chest requires 9 hours of labor, and a table requires only 6. However, a chest requires a 21 board feet, and a table only requires 18. So now the problem starts to get a little more complicated, because if we were to try to figure out, how many hours of labor per unit profit, it would start to get confusing. So one approach to solve this problem is to formulate it as a linear programming problem, and then use established methods to go in and solve the problem. So we can see what our resource requirements are. So basically, a summary of this process is we first have to identify the decision variables. So that's a simple question. One is, how many chests and tables should we produce? The second is we have to create an objective function, some objective that we are trying to either minimize or maximize. And the third step is we have to define the constraints. So basically, how many resources do we have available? In this case, it's lumber and labor. So management first has to determine how many chests and tables they should make. And these are what we refer to as their decision variables of interest. So because management does not know what these values are, they can represent them symbolically and solve for them later, much like you learned how to do in your early algebra classes. If you don't know the answer to something, just specify it with a variable. So in this case, we're going to specify these values with x1 and x2. So these are our unknowns, the number of chests and number of tables to produce, x1 and x2. So the objective for the woodworking company is to maximize the profit. So profit is determined from chests by multiplying the number of produced chests by the individual profit for each chest. Likewise, the profit for the table, you multiply the number of tables by the individual profit. And these values are $2,900 for a chest and $2,300 for a table. You might be thinking to yourself that these are rather large numbers, but if you've ever dealt in antique furniture, you'll know that these numbers are somewhat reasonable. So the total profit can also be expressed symbolically using the variable z. We usually specify capital Z as our objective function, and we can express it mathematically as 2,900 times x1 plus 2,300 x2. So while we don't know what the maximum value of this function is, we do know the value as a function of x1 and x2. So if we increase x1 and x2, this value will increase accordingly. So placing the term maximize in front of the profit equation, we express the objective of the company. It is to maximize total profit. So we would like to maximize Z, where Z is equal to the total profit per week, and our profit from chest is 2,900 and profit from tables is 2,300. So now we have to look at our constraints, because this is ultimately what is going to determine what our maximum profit is. So if we had an infinite number of constraints and an infinite amount of demand, ultimately our profit would be infinity, but we know that this isn't the case. So let's first look at our labor constraint. The two resources are used in the manufacturing of the products, wood and labor, both of which are limited. So each chest requires 9 hours of labor to produce. So therefore, the labor used to manufacture each chest is 9 times x1, or 9 times the number of chests. Likewise, each table requires 6 hours of labor and can be represented by 6 times x2. So therefore, the total labor used by the Eager Beaver Woodworking Company is the sum of the individual amounts of labor used for each product, or it's going to be 9x1 plus 6x2. Now, the problem is we have a limited amount of labor, and we have this is due to we have a finite number of workers that are performing this task. So the amount of labor represented by 9x1 plus 6x2 is limited to 180 man-hours of labor each week. So therefore, the complete labor constraint is going to be 9x1 plus 6x2 is less than or equal to 180. We use the less than or equal to inequality that indicates that's the maximum amount of labor that we can utilize. So we don't have to use all 180, but we can use no more than 180. So this constraint allows for flexibility for the company. They do not have to utilize all of the 180 hours and may have idle or excess capacity. Now let's look at the lumber constraint. The constraint for lumber is formulated in the exact same way. Each chest requires 21 board feet of lumber and may be algebraically represented by 21x1. Each table requires 18 board feet of lumber and can be represented by 18x2. So given that the amount of lumber available for production each week, we have 504 board feet of lumber. This constraint can be written as 21x1 plus 18x2 has to be less than 504 board feet of lumber. So one final but very important constraint is what we refer to as a logical constraint or non-negativity constraint. And it may be common sense to us. The problem is when we start solving these formulations using the computer may not see this as obvious. So we always need to be aware of this and include these constraints. Basically, we're saying that x1 and x2 have to be positive values. You can't have a negative number of tables or negative number of chests. So we have to ensure that x1 and x2 are both greater than or equal to 0. So in the context of a linear programming model, the complete model is described as what you see here. That we want to maximize z equals 2900x1 plus 2300x2, subject to our labor constraint, which we see here, 9x1 plus 6x2 less than or equal to 180, our lumber constraint, 21x1 plus 18x2 less than 504, and our non-negativity constraint. So this is a complete linear programming model in the context of operations research or management science. So in previous modules, we discussed the different types of models. We said that some models can be charts, it can be graphs, it can be flow charts, it can be procedures, or other types of models. But in the context of linear programming or operations research, this is considered a complete linear programming model. So anytime you hear model in terms of OR linear programming, think of the model as having this format: an objective function, constraints, and obviously we have to have decision variables, because this is what we're going to be solving for. So now that we've developed the model, let's discuss how we're going to solve it, because developing the model, while can be difficult, especially for very large problems, is useless unless we implement some procedure to solve it. But oftentimes developing the model can be a difficult part of the whole model formulation process. So one way to solve the model is simple trial and error approach. We can pick different values of x1 and x2 and plug the values in the objective function until we get a maximum value. I think we can see that this is a very inefficient procedure. Ultimately, what we would be doing is, picking values, say, of x1. Let's suppose we picked, say, 5 for x1 and say we picked 6 for x2, we could go in and solve this, that 2900 times 5 is equal to 14,500 here, and then we could take 2300 times 6, that's equal to 13,800, and if we were to add these together, we would get 23,000 or 28,300. Okay, so this is a feasible solution, but is it the best feasible solution? Well, I don't know if it's feasible yet. Let me actually take a look. 9 times 5 plus 6 times 6 is 81, so yes, we don't use all of the man hours, and 21 times 5 plus 18 times 6 is 213. So we didn't use all of our resources. So this would be a feasible solution. I think we can all see that 5 and 6 isn't the optimal solution. So a trial and error approach probably isn't the best way. Okay? So in order to determine the feasible solution space, or what are the possible values that this model, or the values for x and y, such that all of the values are feasible, this is referred to as a feasible solution space. So we must first plot each of the constraints on the xy axis as shown in the following figure, and this is done by treating all constraints as equations or straight lines and plotting them on a graph. So let's first consider this equation right here. So we have two variables, x1 and x2. If you think of x1 and x2 as x and y, we can see we can easily plot this on an xy plane that you see here. So we could plot, let x1 and x2 be x and y, and plot this this line or this equation on this graph. So how do we go about doing this? Well, determining the x and y intercepts is the first step in plotting this equation. So if you have 2 points, then you can draw a straight line through those 2 points. So fortunately, there's an easy way to construct the xy intercepts for any line. And the first point can be found by substituting x1, letting x1 be equal to 0, and then simply solving for x2. So if we let x1 be equal to 0 and solve for x2, we see that x2 is equal to 30. So this is the x2 or the y-intercept. Now let's solve for the x1 or x-intercept. We let x2 be equal to 0, solve for x1, we get x1 is equal to 20. So this yields the coordinates 0, 30, and 20, 0 for the 2 points, and then the line representing the equations is drawn by connecting the 2 points as shown in the following figure. So this is a graph of our first constraint, of our labor constraint. Okay, and the constraint is represented by a region, not as a line. So we just let it be a simple equation so we could get the 2 points, but because this is an inequality, a region is going to specify the feasible solution space, not a line. So when we use the less than symbol, we can see that actually this area here is valid for this inequality. Okay, so it's not just a line, it is an entire region. So if we look at these 2 points, we see point A and point B. Point A is located at 4, 10. So let's take a look. If we plug in the values of 4 and 10 for x1 and x2, we can see we get 96. So 96 is less than 180. And we can see this by observing that point A is in the blue shaded region. Now if we look at point B, it is located at what? 15, 20? So if we plug 15 and 20 in for x1 and x2, we see that this value is 255, which is not less than 180. And we can see this, that it is outside of the shaded region. So this is a way to determine if a point is feasible or not. Now this is for our labor constraint. So let's take a look at our wood constraint or lumber constraint. We do the exact same thing. First we let x1 be equal to 0, solve for x2, we get a value of 28. Then we solve for x1 and get a value of 24. And so our points are 0, 24, and 24, 0, and 20, 0.28. Okay. So combining the two individual graphs for both labor and lumber yields a graph of the model constraint shown in the following figure. The shaded area in this figure is the area common to both model constraints, and this is the only region of the graph that will simultaneously satisfy both constraints. So what we're ultimately doing is we're taking the intersection of this region here with this region here. And when we do that, this is what we get. That we see that this area here is the area common to both constraints. So any point in this shaded region, or this light blue region, is a feasible solution. Is it the best solution? Probably not, but at least it is feasible. We don't violate any of our constraints. So let's examine points x, y, and z in the following slides. We look at point x right here. We can see that x satisfies both the labor and lumber constraints, and this is known as a feasible solution point. Point y here, we can see, in fact, it satisfies the labor constraint, but it violates the lumber constraint, so it's an infeasible solution. And point z violates both constraints, so it's also an infeasible solution. So we have all the corners of this this region. We can see these are our xy intercepts here, and then we simply let these two equations be equal to one another and solve for x and y, or x1 and x2, and found that they intersect at coordinates 6, 21, and then obviously 0, 0 is our origin. Okay, so what do we refer to this space as? So this shaded region is referred to as the feasible solution area. It's also known as a polytope. And linear programming models with feasible solution spaces create a unique polytope known as a convex polytope. And convex polytopes have unique solution characteristics that allow optimal solutions to be found relatively easily that we'll discuss in another module. So what's the definition of a convex polytope? Well, a convex polytope is a special case of a polytope having the additional property that it is also a convex set of points in the n-dimensional space. We denote this space as capital R raised to the n power, meaning that this is the n-dimensional space. Okay, so in Euclidean space, an object is convex if for every pair of points within the object, every point on a straight line segment that joins them is also within the object. So a convex set along with the non-convex set is shown in the following figure. So these definitions are a little ambiguous unless you really understand what convexity and non-convexity means. So the easiest way to understand what they mean is to look at a simple graphic, and then it becomes instantly clear. So if this is our region, this green area, how do we determine if it's a convex set? When a convex set, you can pick any 2 points as long as it's not the same point, but I guess even then it wouldn't matter. You pick any 2 points, so we'll say we're going to pick x and y, and this is for any dimensional space, so not just 2 dimensions or 3 dimensions or dimensions we're familiar with in dimensional, so it could even be 100-dimensional space. So if we can pick those 2 points that are within that space and draw a straight line, and if every point on the line is in the space, then we refer to it as a convex set. And this polytope, this would be a convex polytope. However, if we pick 2 points, can be any 2 points, and we connect them with a straight line, and part of the line actually falls out of the polytope itself, then this is referred to as a non-convex set. So in the context of linear programming, you will only deal with convex sets. Not all problems are linear problems, or can be formulated using linear programming. So in more advanced models and OR techniques, you will deal with non-convex sets, but in the context of linear programming, all polytopes are convex, and it makes the problem relatively easy to solve. So obviously there's a relationship between the polytope and the optimal solution value. So in the next module we're going to examine how to determine the optimal solution to a linear programming formulation using what we refer to as the graphical method. So what I would like you to do is refer to any handouts supplied with this module, maybe handwritten notes or spreadsheets. If available, refer to the optional reference chapter in the textbook. Make sure you complete the assigned homework relating to this module, and review any lecture, presentation, and notes pertaining to any questions that you may have about the material covered in this module.